Hello and welcome. So today we're talking about section 3.1, section 3.2, and a little bit about Appendix D1. We're covering quadratic expressions in Appendix D1, but then the bulk of class is talking about quadratic functions. Okay, so far we've been thinking about linear relationships represented by equations like y equals mx plus b. Here we have, an intercept, and we have some constant rate of change, the slope, that connects these two variables. Remember, so a 1 unit increase in whatever is the x creates a m unit increase in your dependent variable. These are straight lines. We're thinking of straight lines through the xy plane. So then the question is, what if we want to graph a curve? Now what do we do? Well, clearly we have to do something different. So here we have a quadratic function. So first I'll introduce the theory, then we'll see some example. Quadratic function in x is one that can be written in standard form. So just like we had a standard form for a linear function, which was ax plus by equals c, we have standard form for a quadratic function. It's ax squared plus bx plus c, where a, b, and c are constants, and a can't be equal to 0. Why? Why can't a be equal to 0? Well, if a is equal to 0, our square term drops out, and we just have a linear function, right? This is the linear term. So, okay, the term ax squared is the quadratic term. Its coefficient, sorry for the possessive, or I mean for the contraction, this should be possessives and no apostrophe. Its coefficient a is the leading coefficient. So if a is positive, the graph is a parabola, it opens upward. If a is negative, the graph f is a parabola, it opens downward. And bx is the linear term. Why? Well, here we just have some slope times the independent variable. It's just like we had from y equals mx plus b form. And c is the constant term. It's the vertical intercept on the graph of our function f. Okay, so here's an example. Dude Perfect. So a YouTube sensation, Dude Perfect, has a video where they shoot a basketball from a helicopter, and they make the shot, at least in the one that they have in the video. So here's a equation to represent the flight of the ball. So the height of the ball in feet, t seconds after it's thrown, is given by h of t is equal to negative 16t squared plus 13t plus 128. So what's the practical meaning of our value 128? How can you see this value in the graph of the function? So think about what the graph of the function has to look like. And then what effect does the sign on the coefficient minus 16 have on the graph of the function? So stop the video, think about this, kind of reflect, especially based on what I said on the previous slide, right? Think about this stuff. Okay, and now let's apply it in this example. Well, here's the picture. Here's what this looks like. Hopefully this is the picture you have in mind. I mean this to be about, 128, right? And so what happens? Well, it initially rises, then it falls, it reaches a peak, looks like around 1 second. What's the interpretation of this 128? Well, that's the height of the helicopter, isn't it? Right, so the constant term 128 gives the height of the ball when the ball is released at t equals 0. Right, so plug in t is equal to 0. These terms drop out. We're left with h of 0 is equal to 128. That's the height of the helicopter when the ball is released. That's the interpretation here. And that's because the quadratic function has a vertical intercept of 0, 128. Right. Okay. Now, since the coefficient minus 16 is negative, that's telling us that this thing is going to open downward. And this minus 16t squared is going to counteract the two positive terms. So the graph goes up at first, and then it's going to reach a maximum, and it's going to go down as the ball approaches the hoop and goes in at t is equal to 4. Okay. So here's another thing we can do. Let's make a table. Let's get a table for the height of the ball in each of the first 4 seconds. How do we make a table? Well, we're going to evaluate h of 1, h of 2, h of 3, and h of 4. So stop the video, go ahead and just evaluate this function. Find h of 1, h of 2, h of 3, h of 4, and build a table. And here's our table, right? So if you plug in 0 for t, the h of 0 is 128. Plug in 1, you're going to get 144. Plug in 2, 128. 3, you're going to get 80, and then 4 evaluates to 0. Right, because you're going to get it exactly balancing out, and then if you were to plot these points, you're going to get that. You're going to get the graph. That's where I got the graph from, right? All right. You could also do this with your graphing calculator. Okay. So here's another example, just thinking about other quadratic functions. Let's write these things in standard form and then identify the coefficients a, b, and c. Okay, so if you forgot what standard form was, we just introduced it. All right, standard form, ax squared plus bx plus c. So go ahead and write that down. Ax squared plus bx plus c is standard form, and a, b, and c are our constants. They're the coefficients. Okay, so get these guys into standard form. These are actually presently in factored form, and we'll talk about factored form in a little bit. The next thing you want to do is evaluate f of 0, f of 0.5, f of 1, and then describe the graph. And then evaluate g of 0, g of 0.5, and g of 1, and describe that graph. So you can pause the video. Go ahead and do that. Okay, so now resuming, well, we can just distribute. So 2x times x is 2x squared, 2x times minus 1 is minus 2x. So a is 2, b is minus 2, and c is 0. That's legal, right? So c is 0. There's no constant term. C is 0. Think about what this tells us about the graph. Remember, c is going to correspond to our vertical intercept. All right, so what about this one? We evaluate, or we distribute and then evaluate. So we get x squared minus x. We distribute, and we see a is equal to 1, b is equal to minus 1, and c is equal to 0. Okay, thinking a little deeper, let's evaluate f of 0, f of 0.5, and f of 1. And describe the graph. Well, the first thing we can observe is, we're going to have a is positive, right? Our a term, actually in both of these, our a term is the coefficient on the square term. That's positive, right? It's positive in both cases. So we know for sure this thing's going to open upward, which means the vertex, the bottom of it, is going to be a minimum. Otherwise, it could have opened downward, and then we'd have the maximum point, like we saw with the dude perfect example. Okay, so if we evaluate, just plug in 0 for x. I mean, by the zero product property, since you have a product, two things multiplied by each other, and this one's 0, we know f of 0 is 0, so that's not a surprise. F of 1/2, well, you can plug in 1/2. 2 times 1/2 is 1. X minus 1 is minus 1/2, right? And then you can do the same thing with 1. 1 minus 1 is 0. So this particular curve opens upward with its lowest point at f of 1/2 at minus 1/2. And we kind of know this because this is symmetric. So look, we have f of 1, and if we go a half unit, closer to the origin, to the origin, we go a half unit away from the origin, right? We reach our minimum. So what does this thing look like? Well, it's sort of going through the origin and then opening upward with a low point at minus 1/2. Okay. What about the other one? Really similar. It's just a shallower curve, right? We know that because look at how these things are related, right? We just multiplied this one. Well, going from here to here, we multiply by 1/2. So 1/2 times 2 gets us g of x. So 1/2 f of x gives us g of x, or 2 times g of x gives us f of x. That being the case, we know they're essentially the same curve. One's just shallower. And sure enough, we see this. G of 0, just like f of 0 is 0, g of 0 is 0. And just like f of 1 was 0, g of 1 is 0 as well. And the same thing, curve opens upward with its low point at minus 1/4. Okay, so moving on to section 3.2. Now we're going to think a little bit more carefully about different forms of quadratic expressions. So we're going to remember I said we were going to talk about factored forms. Let's think about factored form. So we can actually write this expression, h of t is equal to minus 16t squared plus 32t plus 128, as minus 16t times the quantity t minus 4 times the quantity t plus 2. Or if you pause the video, distribute. You can either distribute using the distributive property, so distribute the quantity t minus 4 to t, and then t minus 4 to 2, or distribute the quantity t plus 2 to t, and t plus 2 to minus 4, and then sort of expand. Or you could FOIL, first outside, inside last. So t squared plus 2t minus 4t plus minus 8. And then multiply the whole thing by minus 16. All right. Anyway, so how do we interpret t minus 4 and t plus 2? Think about that. Well, when when t is equal to 4, you get a 0. When t is equal to minus 2, you get a 0, right? So this is going to be when the height is 0. So let's look at this more carefully. When t is equal to 4, the factor t minus 4 is just 0. So it tells us the height of the ball at after 4 seconds after release is 0. Right? Hits the hoop 4 seconds after it's released from the helicopter. What about this one? Well, when t is equal to minus 2, the factor has value 0, but t is equal to minus 2, this means we're going back in time 2 seconds. And that's nonsensical, so we actually don't have a good interpretation practically for this. So anyway, mathematically, these are the zeros of the function h. T equals 4 and t is equal to minus 2 are the zeros of the polynomial. And so more generally, a curve is in factored form if it can be written as y is equal to f of x, a times the quantity x minus some r times the quantity x minus some s. In the example we just saw, a was minus 16, minus r was r was 4, and then x was or s was actually positive 2, and then the corresponding zeros were positive 4 and minus 2. Anyway, so constant r and s are the zeros of the function. That's just where the graph crosses the horizontal axis. And then constant a is the leading coefficient. It's the same as the constant in the a in standard form, right? So when you're factoring, that's something to be aware of. Okay, so here's another form we'll take a look at real quickly. We could symmetrically write this thing as minus 16 times t minus 1 squared plus 144. If you remember this is kind of what you get when you do the completing the square. All right, so we can use this form. I won't worry about. I'm just giving you this for free. We're just going to talk about it, so you don't need to worry about deriving it at this point. Use this form to show that the ball reaches its maximum height at 144 feet after 1 second has elapsed since it's been released from or flung from the helicopter. So given the form, h of t is equal to minus 16 t minus 1 squared plus 144, show the ball reaches maximum height. Okay, so how can we do this? Well, we can just evaluate this thing at t is equal to 0, t is equal to 1, t is equal to 2, 3, and 4. So what I've got here is I've just got this first term in our sum, and then I'm adding 144 to it. Reason why I do it this way is here we can kind of see the behavior of this thing a little bit easier before we add in this 144. Right? Anyway, the high point we see is right here, 144, and that's what we mean by the vertex of the graph. It's either the maximum or the minimum value of the function, depending on whether the graph opens up or opens down. Right? So if a is positive, if this coefficient a is positive, we know this thing opens upward, so then we know our vertex is a minimum. If a is negative, we know this thing opens downward, it's an upside down U, and then we know our vertex is a maximum. Indeed, that's what we have here. This thing opens downward because our a is negative, it's minus 16. Therefore, our vertex must be a maximum. Okay. So more generally, a quadratic function expressed or in x is expressed in vertex form if it can be written as y is equal to f of x, a times the quantity x minus h squared plus k with constants a, h, k, and a can't be 0. Why can't a be 0? The same reason as before. It makes this thing not work. Go see what happens. This drops out, and then we just have this whole thing is equal to k, right? So that's not as interesting. All right, f of h equals k, and the point hk is the vertex of the graph of f. The coefficient a is the leading coefficient. It's the same as the a we had in standard form. Right? Remember, standard form was just ax squared plus bx plus c is equal to f of x. Again, if a is positive, then k, our vertex, is the minimum value of the function, and the graph opens upward. If a is negative, then k is the maximum value of the function, and the graph opens downward. This is just the sort of more formal, more rigorous way of saying what I had just previously mentioned. Okay, so the next thing we're thinking about is how can we construct quadratic functions based on the things that we've now learned, based on these larger ideas. Well, we know different forms give us different information about a quadratic function. We have information such as vertex, zeros, and we can build a formula based on this information. Okay, so for example, if we know the zeros are x equals 1 and x equals 4, and the y-intercept is minus 12, go ahead, find the formula. If we know the y-intercept is 0 and 5, and the vertex is 3 minus 13, go ahead and find the formula. All right, so pause the video. Let me go back and show here's our vertex form. You might want to write this down. F of x is equal to a times the quantity x minus h squared plus k. Right? And then our factored form, f of x equals a times the quantity x minus r times the quantity x minus s. Okay, and here's the information that I'm asking you to work with. This right here, we have our zeros, and we have the intercept. Find the formula. And we have an intercept and a vertex. Find the formula. Well, all right, so here this is. We know the zero, so we're going to use factored form. Zeros is 1, zeros is 4, so x minus 1, x minus 4, and then f of x is just equal to a times this stuff here. We know the y-intercept is minus 12. Let's use that information. Y is equal to minus 12 when x is equal to 0, so we know minus 12 is equal to a times, let's plug in 0 for x, plug in 0 for x. This evaporates. This becomes minus 4. The whole thing's not 0, right, because this is 0 times minus 1, so that's minus 1 times minus 4. It gives us positive 4a. Oh, a is equal to minus 3. So then our formula is minus 3 times quantity x minus 1 times the quantity x minus 4. And the negative a means this thing opens downward. All right, so going back, what did I do? I started with factored form. I plugged in the zeros we had. Now I've got this a. I've got one more piece of information I needed to use, this a, and then I've got this intercept. So let's figure out how we can use that. Oh, well, the interpretation of y-intercept is that when x is 0, this thing's going to be equal to 12. So let's check that out. Right. Not when the polynomial takes on a value of 0, when x takes on a value of 0, right? We're finding the vertical intercept. Vertical intercepts have x coordinates of 0, and then a y coordinate, in this case, of minus 12. Okay. All right, so then the next one, if we know the y-intercept is 5, 0, 5, and the vertex is 3 minus 13, find the formula. Hey, we have to use the vertex formula. So f of x, a times the quantity x minus h squared plus k. Let's just plug in those values. Same thing, we've got to find this a. How are we going to do this? Well, let's use the information that we have. Right, so going ahead, well, y is equal to 5 when x is equal to 0. So solving, let's see, we have 3 minus 3 squared is 9 minus 13. We have 5. And move the 13 to the other side. We have 18 divided by 9. A is 2. All right, so the correct graph is going to be f of x is equal to 2 times the quantity x minus 3 squared minus 13. Since a is positive, we know this graph opens upward. All right, so that's pretty cool. At least I think so. Hopefully you do too. All right, so then the last part is Appendix D1. Here I just mean to kind of collect and categorize a lot of the things that we're going to care about for quadratic expressions. I don't have any examples here. I'm just going to kind of enumerate everything that we're going to sort of be taking as given to help us solve these problems. Okay, so first off, an expression of the form ax squared plus bx plus c, standard form, is a quadratic expression. These constants are the coefficients. And a couple facts, well, the product of two linear expressions is itself a quadratic expression, or is a quadratic expression, since expanding a product of the form x plus r, which is linear, times x plus s, which is linear, is always a quadratic expression. Why? Well, let's do this. You can FOIL, or you can expand by the distribution. However you're going to do this, you're going to end up getting a quadratic, right? You have to. How do we know? Well, we're going to get an x times an x, and that's quadratic. All right, and then here I've just collected like terms, or I've factored out the x, and there we go. So the sum r plus s is the coefficient of the x term, and the product rs is the constant term. All right, so don't just gloss over the significance of this. This is important for factoring, right? This is going to help us with our factoring strategy. Remember, when we're trying to go from something like this back to this, we want to think about how these numbers multiply together and interact with the variable to be able to build this quadratic, right? They multiply to give us this term, it's a product, and then they multiply by the x's and add to give us this term, the middle term, the b coefficient. Okay, so they multiply to give us c, they add to give us b. Multiply to give us c, add to give us b, and then the leading term on the x's multiply to give us a. Okay. So to factor a quadratic expression, if the thing's factorable, the following steps work. Factor out all common constant factors, giving us k times something in standard form. In the remaining expression, multiply the coefficient here by the constant term, which gives us ac. Right, so let's multiply whatever this is by the constant term, that gives us ac. If a is 1, that gives us c. Then find two numbers that multiply to give us ac and sum to b. That's the coefficient of the x term. All right, so that's going to require a little bit of thought, a little bit of guess and test, but you should be able to make an educated guess based on, you know, this information we have here. Then break out the middle term, bx, into two terms, using the result of the previous step, and factor the four terms by grouping. What do I mean break the middle term bx into two terms, using the result of the previous step? Well, look at this, right? If these were numbers, we would sum up r plus s. That would be our b. Going in reverse, breaking it back, we have r plus s, then we go from 3 terms to 4 terms. That's what we have in mind. Now, how do we factor this by grouping? Well, let's look over here. We can take out an x, and that'll give us this, and then we can take out an s, and that'll give us this. All right, that's all it is. Okay, so a couple other things. Perfect squares. Here's the expression for perfect squares. A perfect square quadratic is when we have some x plus some r. That thing times itself. So the quantity x plus r times the quantity x plus r, that gives us perfect squares. Also, x minus r squared times the quantity x minus r times the quantity x minus r, or the quantity x minus r squared is also a perfect square. Let's think about this. Think about what happens when we expand this. If we have x plus r times the quantity x plus r, then when we FOIL, or when we expand by grouping, well, we'll get an x times an x, we'll get an r times an r, so those are going to square. But what happens in the middle term? Well, we're going to get an r times an x and an x times an r. That's going to be a 2rx. What about the sign? Well, if this thing's positive, we're going to get a plus 2r plus xr, or a plus 2rx. What if this thing's negative? Well, then we're going to have a minus rx plus a minus xr, and that's going to give us a minus 2rx. So that's all that is. If this is confusing for you, make up some numbers right here. Try something out. Try x plus 1, that quantity squared, and expand it. And see what you get. What will you get? You'll get x squared plus 2x plus 1. All right, so make up a couple of those and do enough so that you see the pattern and you feel comfortable. Okay, how to determine if the expression is a perfect square? Well, an expression with 3 terms is a perfect square if the 2 terms are square, the first and last term, and the third term is twice the product of the expressions whose squares are the other terms. All right, so let's just go back to this. These terms are squares, and then the other term is twice the product of x and r. Right? So these terms are squares, and in the middle is twice the product of x and r. That's all it is. And if you see this, then we know that we've got perfect squares. Now, oftentimes you might have something hidden. You might have something buried where you've got to factor something out. Yeah, maybe you have a common factor, a common coefficient across these. You factor these out, and all of a sudden you've got a perfect square. And so pay attention to that sort of thing. It might not jump out at you immediately. Just look and see, is there anything mathematically legal you can do? If so, do it and see if you have a perfect square. You might. And then the last thing, a difference of squares. If an expression is in the form x squared minus r squared, it can be factored as x squared minus r, or x minus r times quantity x plus r. And you can distribute this, or you can FOIL or whatever, and you'll see, oh, we get an x squared, we get an r times a minus r, or a minus r squared, and in the middle we get a minus rx plus an rx. And the middle terms sum and drop out. Okay, now where's the point of confusion? Don't confuse this difference of squares with this one right here. They're similar, but they're importantly different. What's the difference? Well, here we have a x minus r times x minus r. Quantity x minus r times the quantity x minus r. And then what do we get? Well, we get the middle term doubled. What about over here? Well, we get a quantity x minus r times a quantity x plus r. Now the middle terms have opposite signs, so they don't double. Instead, they drop out, and we just get x squared minus r squared. Okay. All right, so let me know if you have any questions.